Hello. Well, welcome to the final, I guess, technical discussion part of the conference, which is our panel discussion on the overall theme of the conference, which is supercomputing for sustainable development. I'm delighted that Neil Ashton from NVIDIA has agreed to chair the panel discussion, and I'm going to hand over to you, Neil. You can introduce your panel and proceed with the discussion. Thank you.
Well, thanks, Peter, for the invitation and a great job on the actual conference. I wasn't sure if anyone would still be here because this is the dreaded slot, I'm afraid, at the end of a conference when most people are thinking of catching a train or a flight. But clearly the conference has been so good that people have stayed till nearly the end. So yeah, we're going to have a little bit of a panel discussion, I guess, to finish this off. As I said, Neil Ashton from NVIDIA, and my job really is just to ask the questions. But before we get into the questions, I think what we'll do is we'll ask everybody to briefly introduce themselves, who they are, what they do, and then we'll get into the questions. So, Hindumathi, do you want to go first?
Yeah, I get to sit next to you, so I'm first, right? So, thanks a lot, Neil. And hi, everyone. I'm Hindumathi Palanisamy from the World Meteorological Organization. I'm a scientific officer with the World Climate Research Program. So I guess I'm one of the very few, or maybe the only one here, being the end user of the HPC supercomputational community. So what we basically do is coordinate and manage international research on climate science. So trying to understand the various aspects of Earth system components and the impacts of climate change on these components. So HPCs are crucial because a huge part of our modeling efforts, they come from the HPCs, and I'm happy to be here to be a part of this panel discussion. Thank you.
James?
Hi everyone, I'm James Hetherington, Professor of Computational Science at University College London. I run our Advanced Research Computing Centre, which I think what's unique about what we do there is we've really focused on building up in a higher education institution, the professions that enable team-based computational science. So we have 100 and something research software engineers, data scientists, data stewards, research infrastructure engineers, and research managers working together with researchers from across the university to enable trustworthy, reliable and sustainable computational science. We also run some supercomputers, but it's the work that we've done in building up that professional model for team-based computational science that I'm most proud of. More recently, and I think that's what's got me into this panel, I've been working to set up UCL's Grand Challenge for the Data Empowered Society. And what we're doing there is, I'm half of the Pro-Vice-Provost for that, and the other half is my colleague, Professor Alison Littlejohn, who's a social scientist in our Institute of Education. So I'm the computer nerd and she's the social scientist. And we're working together to try to understand how we can bring these communities together to enable, again, effective, trustworthy, and safe, and useful, and empowering, and hopeful transformation through digital methodologies.
Great. Sally?
Hello, I'm Sally Ellingson. I'm at the University of Kentucky in the U.S. I work for an academic cancer center there called the Markey Cancer Center, and I'm a computational scientist that collaborates with our cancer center members. We have teams that range from physicians to computational scientists, so we have large interdisciplinary teams working on problems. I largely work in computational drug discovery and also do informatics to support our cancer registry. Kentucky is unfortunately has some of the highest cancer rates and mortality and incidence in the U.S.
Florina?
Thank you very much. I'm Florina Ciorba. I'm a professor for high-performance computing at the University of Basel in Switzerland, so not far from here. I am just a computer scientist, but of course I have very strong collaborations with computational scientists in the region and of course also outside Switzerland. And my expertise and my group expertise is in optimization of workloads from all domains. We have been running for a few years a collaboration with astrophysicists and cosmologists, where and the Supercomputing Center in Lugano, where we have developed a code that can simulate certain evolutionary processes in the universe. And as we are thinking of optimizing and, of course, studying certain important applications for cosmology, astrophysics, and large-scale simulations for computer scientists of interest, we begin to think of how much energy and carbon emissions all our simulations are producing, in addition to the insight for the communities involved. So, yeah.
Great. Okay, well, maybe if they go to the next slide, doing a little bit of research for this panel, the title is Supercomputing for Sustainable Development, and the idea is to look at these 17 goals. And I was thinking we could have done a quiz on this, but I'm pretty sure none of you know all of these 17. And you're probably more, like probably many of us have focused on, is the energy climate question, but the meaning of sustainable development goals is more actually than just the climate and weather, but goes from poverty to infrastructure to economics, obviously to climate action. So we're not going to be able to cover all 17 of those, but I put this up partially as a cheat sheet for us, so we know what they are, but also for you, because we will probably go around and have a little bit of a discussion for the next 25, 30 minutes. But then there's an opportunity for you to ask questions. And so that could be on any of these topics. So yeah, have a look. So it's a bit of a cheat sheet for you all. So I think maybe the first one, which is probably the obvious question to ask, but I'll ask it anyway, which is, do you think HPC can have an impact on achieving these goals? And if so, could you perhaps give an example of where you think it has or it has the ability to do it? And maybe Sally, do you want to go first?
Sure. So, really exciting research in the area of digital twins and the promise for personalized medicine. The problem space is just huge with, we have 20,000 protein coding genes, which is maybe an order of magnitude or more actual protein conformations in an individual, and a huge potential chemical space. Just it's such a large problem, and HPC would be needed to tackle it. And because it's such a huge problem, going towards more sustainable computing would be really important to reach those goals.
But are we any closer to that dream of personalized medicine, where, each person, instead of just getting some generic drug that's been developed for an average person, I guess, that it's more tailored to you? Have you seen any progress towards that?
There's certainly treatments that are developed for specific mutations that are known to be common, but for truly personalized medicine, when you're looking at the variations and at the individual level, we still have, ways to grow in that area.
Okay. How about you, James?
So first of all, retroactive plug for the mini symposium we did earlier on trusted research environments. One of the things we're going to need to do in order to bring the power of supercomputing to bear on those personalized medicine challenges is enable healthcare ecosystems to allow patient records to be used within supercomputing environments, and there's a lot of complicated governance and security work we need to do to enable that, and that's something we're looking at in a number of projects around the DARE UK program of what do we need to do in order to get the kind of environments that we used to, which are heavily governed for working with patient data, and bring the power of supercomputing into those. And I think that's going to be a key part of that story. Of course, one of the biggest successes that we've experienced recently for the use of HPC in saving lives was the use during the COVID pandemic. So during COVID, I was one of the chief data science advisors in our biosecurity, health security agency, and we were running the models that were working out things like, our numbers and, which towns to lock down and that kind of thing, right? And it's scary because computational science went from being a thing we do that's quite fun from a scientific perspective to making real life or death decisions and profound impact both through health and economics on people's lives. this is one of the reasons why I care so much about making sure our code is trustworthy and reliable and well-engineered and well-written, why the research software engineering story has been so important. Because for all of these, if we are going to use computational science to help solve these challenges, many of them are political footballs. Doesn't take much of a mistake in our software engineering to invalidate the conclusions, and we've lost our public trust. So good engineering is really important.
I'm actually sure, are the mini symposiums going to be online? I guess they are. If we didn't get to go to one, the recording's probably going to be around, isn't it? So that's probably a good thing, because most of us can only go to one. And by definition, you can't go to the other parallel ones. So, yeah, probably a reminder to go to the platform and actually spend the next few days catching up. But how about you, Florina? How do you think HPC has impacted on these?
So that's a very good question, and thank you for providing this cheat sheet. It is overwhelming to even think that all of these are goals and that we have to be mindful of them whenever we conduct our academic research and activities. So I had the time, thank you to the previous answers, to think about two goals. So HPC can help in the sustainable goals, for instance, for goal 12, responsible consumption and production of energy. So not necessarily in the production of energy, although these days for water-cooled supercomputers, right, the hot water is used to heat different facilities and even cities. So there is a responsible production as well, maybe of thermal energy. And the responsible use is where I think supercomputing systems these days and the community overall is being much more active in measuring, because without measuring we cannot improve, in measuring, in reporting, and in optimizing. And of course the European Union, for all its Euro HPC supercomputers that they are funding through these initiatives, they are asking all supercomputing centers to report their power usage effectiveness, which this is again mindfulness and actions with concrete results for this goal. But, and without being the expert, I think Hindumathi can speak on that more. For instance, one of the workloads that I know is very, very actively worked on, at least in Switzerland and of course in Europe, are the climate codes, weather forecasting and climate codes, and this can help in goal number 13, which is a very good number. I don't think it's a bad luck number. I think it's a great number to help us advance the models, advance the outcomes that these models produce in order to really address climate earlier.
Great. And last but no means least.
Thanks a lot, Florina. That was a very good, transition to what I wanted to mention. And if you take a look at the SDGs here, HPC is in one way or another involved in all of these SDGs. And today, being a climate scientist myself, I would like to focus more on SDG 13, climate action. Climate change is a threat to sustainability. So if you want to do something about it, we need to have a better understanding of what exactly is happening within this Earth system. And the Earth system itself is not just one single component. You have the land, atmosphere, ocean, cryosphere. So how can a person sitting maybe in front of a laptop, write equations, complex physical and mathematical equations, trying to put them all together, the processes together, to understand what exactly is happening? Especially when we talk about something very transient, the emissions, they are not constant, they keep changing, and we have been accelerating the amount of emissions that humans as such we are producing. So all these things, we can't just sit and work it out of nowhere. We need computers, supercomputers, especially if, just like Florina mentioned, it's not only about early warning forecasting, but also trying to understand what we are going to be looking into the future, projections. And for projections, if you want to know what is going to happen in the next decade or the next century, you need simulations, models, telling us what is going to happen with respect to each of the variables of the Earth system component. And also not only just this, it's also about how much we know in terms of defined processes. We do have observational records that span over decades in the past, and it's going to continue into the future as well. But these observations may not actually focus on the process details, because the resolution does not cover everything that we need to know. And models are able to do this. there needs to be a fine balance as well, you know. Are we going to be producing thousands of simulations to be able to understand something at a kilometer scale level? 2 kilometers, is it really needed? Are we going to use that much of energy to do all these things? Or are we okay with understanding something at a 50-kilometer range? Does it give us enough information? So all of these things are around supercomputers, and I think this answers.
Great.
Thank you.
Well, I think one of, actually, to be fair, Peter mentioned this before, that some of these goals are all positive in the sense that using a HPC machine doesn't, well, maybe someone will correct me if I'm wrong, but doesn't itself maybe cause hunger issues. Whereas research, let's say, on better crop yields or something could improve, you know, the ability to create food and therefore. But the energy one is probably the most one where there's a benefit, but also a potentially harmful aspect to it. So it's probably one that we can talk about a little bit more, because I think it's quite relevant as a debate on that topic. And I think, James, one of the things you mentioned to me, and I'm sort of feel bad that I hadn't thought about it myself, was when anybody who uses a HPC machine knows the queue is your enemy, and you have to figure out a way of getting to the first in the queue. And that's basically, from an end user perspective, your job. But from a sysadmin point of view, you're trying to manage this chaos and trying to have, you know, fair share scheduling and all the rest of it. But one of the things you brought up was about energy, and I think both of you brought up about energy-aware scheduling, the fact that at certain times of the day, the machine may be using more energy, or even more geographically, you could have places that use more or less. So could you maybe talk a little bit about that first, and maybe you could comment on some of this?
Unfortunately, I'm not going to be able to attribute this work properly, but there's a project called the Climate Aware Task Scheduler, which won the prize at the UK Software Sustainability Institute workshop a couple of years ago. And what that does is really interesting, because it turns out that, so we know that certain jobs make machines run hotter, right? It's not the case that the thing's always burning the same energy. But we can actually link the information from, I say this wasn't my work, but I was on the prize panel that awarded the prize to this work, so which is why I'm quite partisan to it. We can gather data on the carbon intensity of the current electricity supply. So people probably know now that, you know, in California the grid is like almost entirely solar in the daytime, but they haven't got enough storage, so it switches to other fuel sources in the night, and there's this kind of thing. And on a sunny, windy day in the UK, we have carbon-free electricity supply, apart from a little bit of gas base load. So we could actually use this information to control when the hot jobs are running according to what kind of electricity is in the machine. It's not a massive effect, but it's a really interesting example of something we can do by bringing all that data that's available to bear.
How about yourself?
Right. Thank you for that. I think it's very important to know, as I mentioned earlier, when you can measure, you can reason about how to optimize job allocation, but also how users themselves can be aware of not only the time limit requirement that they need to ask from a system to allocate to their job, which even that is questionably accurate, notoriously inaccurate actually, but the energy, right? If we don't tell the users how much energy their jobs require, they won't know for the next submission either, and also how much carbon was emitted. But I think it's hard. It's hard because, you know, there are some political constraints in the systems reporting, their power usage effectiveness, their carbon intensity at the country level, or they're at the location level. So it's hard, but it's necessary, right? And it's not a luxury, it's really a necessity. I just want to point out that recently I stumbled into a paper, the name is CODEC, Computational Decarbonization, but this paper positions the CEP theory, conjecture, the carbon efficiency, energy efficiency, and performance conjecture, which is similar to the CAP conjecture in distributed systems, CAP standing for consistency, availability, and partition tolerance, right? Briefly explaining that when you have your data in the cloud providers cannot optimize for all these three, so typically they optimize for availability and not for consistency. So if you lose your data in the cloud, it's going to be available but not consistent. But here we have to be aware that carbon efficiency, energy efficiency, and performance are in an impossibility conjecture especially, as was mentioned earlier, when carbon is not, or the energy produced is not entirely carbon neutral, so there was brown or a black component in producing it, and the carbon intensity fluctuates over the space of a country and over the time in a particular location of the country, right? So I think it is time that we put that onto the way that we design our experiments as computational scientists or computer scientists working with them. And you mentioned earlier in the conversation the idea of a meta-scheduler, right? So in computing systems in the cloud, the cloud provider does that for you. In HPC centers in the academic domain, there is no one meta-scheduler across the HPC centers, but I think there is one. There's not a software meta-scheduler, it's actually the human, right? The human, the PI, the principal investigator, and their collaborators can decide to which system they would like to submit their jobs, and they can look at things such as carbon intensity and PUE to make that choice.
It does make me think, though, that even though it may not be done, the sort of meta-scheduler idea is an appealing one. Because if you ignore, supercomputing center politics and who, wants their machine to be better and more utilized and funding and all the other stuff that I'm sure goes on, you could imagine that an aggregate demand, you could probably better fill the capacity if you had the ability to funnel jobs into unused systems rather than only being on a single one. So it is an interesting debate, which I think certainly in the cloud world, the need to grab GPUs for AI training has made certain people create these sort of meta-schedulers themselves as a company just to find capacity. But maybe just turning on to a slightly different topic that maybe has had its most success with drug discovery and climate is the AI question, because
I do have a question before we move into.
Yes, please.
It's kind of related to. I was just wondering because for climate modeling efforts and it depends on the infrastructure available. So all of these climate-aware task scheduling for, let's say, modeling initiatives within one of the main aspects that we talk about is the CMIP for the projections into the future. So most of them come from countries that have the infrastructure to do these task scheduling, right? So when we think about countries that are usually highly vulnerable to the impacts of climate change, but do not have this infrastructure, how do you think, this is a question, I'm sorry, I'm going to play your role.
Please.
How do you think we can, try to find a way to make sure there is a kind of balance between what is available to whom and what is not available?
Yeah, so I think that approachability and inclusivity of computational science, and South computational modeling and that kind of thing is a really important point. It's one of the things I worry about in terms of a lot of us say, and I still agree with this, that people have a duty to write efficient code because that way you're making better use of the facility, and the facility are expensive and have environmental costs. But on the other hand, the more we say, unless you're writing the most perfectly fine-tuned Fortran, you're not allowed, and all those pesky Python programmers should get lost from our lovely supercomputers. I'm paraphrasing, I know, it's an example. Then you're creating an entry barrier, you're creating a gatekeeping effect on these methodologies. And I think we need to be careful of that, right? Balancing the duty to work efficiently with a desire to be a welcome and opening community to people who are dipping their toes into computational science and are working their way up through the pyramid of scales of computational complexity. Not a thing that I've concluded in my own mind either, but I worry about sort of barrier effects from making it harder for people to get into it.
So my take would be open source software development, because we cannot relocate carbon intensity or footprint, maybe yes, but the intensities we cannot relocate. So I think we have to share the knowledge, and that's the power of free and open source software development that I think this community is very well known for. And sharing those methods and connecting with those communities who are more in need, more urgently in need of these solutions, carbon-aware, task-aware, meta or not meta schedulers. I think that's easy to do, and I hope we are doing that. If we're not, we should pay attention to that even more.
Thank you. Over to you, Neil. Sorry.
That's good. So on the AI side, maybe the broader question is AI a force for good or a distraction within the HPC community? I would be interested to get your thought in the sort of drug discovery world, because arguably, drug discovery was one of those first things that brought AI for science to light. So do you think overall it's been a good and helping to reach some of these goals, or has it distracted from some more traditional HPC use?
I think that there's lots of promise in AI and, maybe a little bit of distraction with the hype, but the things that are really important to remember is that AI isn't perfect, neither are humans. It's trained on data that was potentially labeled by humans, and that, there's still lots of useful cases in healthcare to use AI to be better, to make things more efficient, and they might not always be perfect, but we need to understand the particular setting they're used in and the tolerance and, the trade-offs between, and always have humans in the loop. Even if it's something that can go to production without it, there always needs to be continued validation for it.
Oh, and what about on the weather climate side? I mean, obviously there's been pretty big breakthroughs on that.
It's the hottest topic in the field of climate and weather, at least for now. What we think is that AI can't act independently. It is still dependent on the climate models or the human-based outputs, because what we call as AI emulators, which are like very new things and that are being still tested in both weather and climate domains, is that it takes the output from climate models that have been running for years, simulations of the past, present, future, and also the observational data, and it looks for patterns and relation between the input and the output. And using these things, it's able to produce a result that would correspond to what we need. But then, as I mentioned, it cannot be independent, at least for now. And what I would say is it's a kind of, an output methodology to run things fast, to make it efficient. So what might take a few days or weeks for a supercomputer to produce in terms of a simulation might be very fast. And this would be an excellent tool for policymakers and stakeholders, because if you want to have a result of, let's say, what is going to happen with respect to sea level variation in this particular city in the next decade, they might just visualize it with a tool, simple tool, and AI is for this, at least for now. So are we expecting this to take over? I'm not very sure. But it depends. It takes time to know what exactly it's able to do. Thank you.
Yeah, it certainly does seem interesting, because one of the benefits of very fast inference is, at least in my area of fluid dynamics, the inference is fast, but also it's essentially lower cost and lower CO2. So at inference time, it is even more efficient. The question, and I haven't actually seen a paper look at this, and maybe there is the amount, the full cycle of generating the data, training the model. What's the efficiency of that?
So I think, always in these things it's useful to separate the different bits of AI and machine learning into different labels. One of the bits that's absolutely wonderful for computational science is proxy models, where we train the Gaussian process or whatever with the results of lots of computational simulations, because it allows us to use those simulation runs to get the maximum information at the minimum cost, right? So all these multi-fidelity models where you're actually using information theoretic methods to say, I'm going to run some things on the exascale and some things, well, not on my laptop, but some things at different scales, such as to optimize it's a design of experiments problem, such as to optimize the run to get the information that's represented information theoretically in what happens in your proxy model. So that's splendid, because it increases the marginal utility of large-scale computing facilities. So people are worried, we're not going to run it, there's not going to be enough jobs to fill the supercomputers because it's just going to be all AI. That's not how it is, right? Because that's not how economics works. It increases the marginal value of the capability by getting more from less. So that's fantastic. So that side of ML is fantastic. I also think, although many colleagues disagree with me quite strongly, that the LLM space within AI is also fantastic for us, many people hate it, because what's happening to AI-assisted software engineering, I think, if we're careful, can be really powerful for effective, trustworthy software development at the complicated scales of trying to work in computational science. I don't know if this is going to turn out to be right. There's another world where, vibe coding postdocs type in random code and all of our computational science is invalid and horrible and rubbish. I don't want to be in that one. We're at the decision point on that at the moment. But if we can use LLM-assisted software engineering in doing computational science well, again, I think it will be a really powerful positive for the sector.
I actually saw, I don't know if he's here or not, but Freddie, who's at Texas A&M, showed me something before, which I thought was absolutely amazing. I can't remember the name of it now, but it was a website basically where you could go in and put in some floating point operation, some sort of, maths, and then it would tell you a more efficient version of it. We're not yet at, hello ChatGPT, code me up an adaptive mesh and distribute it, right? Yeah. But the point of the power of some of these is not, I guess most people's use of these LLMs, or at least my naive initial use is, hey, I just want to write some Python code to do something, can you just do it for me? But actually the question of making your code more efficient is probably actually a more valuable way. But how does that play into, I guess, the more traditional role of, and this may be for both of you, but I'll let you answer it, like the role of researchers to come up with better methods and algorithms? Is the AI a sort of friendly helper still with that?
That's a good question. So let me tell you what AI means for HPC. From my point of view, AI is a software accelerator. We have the hardware accelerators, GPUs, TPUs, DSPs, you name it. We've always had them. This is a software accelerator. So you put an accelerator in the software, but just like in the hardware space, it will require silicon. Here it requires memory, space in the memory. It is lines of code. It requires integration, as you need to integrate the CPU and the GPU. It requires integration with existing software that these AI components, whatever their type is, accelerate, right? So I think it's a very powerful accelerator, just like when first GPUs came out, and you're now with a company that has been very successful in deploying them and their adoption. It takes time. It takes training users on how to use AI for good, for societal good, not for curiosity and fun, or for burning cycles, right? So it's a software accelerator, and if we think of AI as not the GPU solve everything in the world, do we not still need CPUs? Yes, we still need CPUs, so it's important to remember they are an accelerator and not a replacer, right? We still need climate models based on physics and other sciences. We need biological models implemented in simulation, so they will never go away. But for HPC performance optimization and system maintenance, actually AIs are becoming a very useful tool. Maybe also in the accelerator sense, but actually in enabling, because if we see the supercomputers as a system generating a lot of data, not only the planet generates a lot of data, right, or the human body, so does a computer system generate a lot of data that has become so complex to analyze with classical tools. So if we build digital twins of supercomputers, we are going to have more efficient supercomputers to support all of these goals. So, but your question was not about that. I answered it. I answered my own question. The question was about algorithms, right? Can we come up with more efficient algorithms? And unfortunately, a company is actually faster at that. The company that started AlphaFold, AlphaCode, AlphaFold, AlphaGo, AlphaCode, now they have AlphaEvolve. And actually, they're launching a pilot project of people who are interested in being one of the first beta testers. So they say, because they produce the most efficient matrix multiplication algorithms by learning from existing matrix multiplication algorithms, and they were able to change a few operations and get a more efficient solution for that problem. So I think they're evolving this to all kinds of algorithms in an evolutionary algorithmic way. So start with your problem, and then they will try out different solutions, and the goal will be more efficient software contributing to all of this.
One of the, maybe a high-level question is around the people's recognition, maybe, of HPC. And maybe this is more for you, as you admit, it's not in the weeds of HPC. Do people value HPC? and this probably goes into more philosophical debate that probably some people hate and some people like, which is supercomputing versus HPC, is there any difference between them? And should we claim AI as our own? Because you have to train a model on a HPC system. I actually think you can. So instead of it should be supercomputing, we should be able to say, well, we're enabling AI as well. But is HPC valued within your company?
Yes. In the field of climate science and also, weather science, HPC is crucial. And people do recognize it, maybe to an extent that there used to be a lack of awareness with respect to the energy consumption and the carbon footprint due to the HPC usage. So, and this is slowly starting to, get introduced in the field of climate science at least. So, for any of our future model simulations, there is a special task team, as we call, looking into the different aspects of how much of the carbon footprint comes out of these and how we can reduce. And it's not only about it, the data storage, the amount of data, the capacity coming out of this, and how we could reduce all these things. So I would say that it's highly recognized, maybe to an extent that, over-recognized and overused. So there is now a sort of awareness to try to reduce the usage in a way to, reduce the number of simulations, or, as I may say, unnecessary high-resolution simulations. Do we need this to,
Yeah, I guess that's maybe the bigger debate, which is, should we worry about the energy usage of a HPC if it's creating so much value for good, or should we be concerned about, are you capping the ability for it to find new discoveries by sort of worrying about the energy usage of the systems? Maybe to make sure we're making this a bit interactive and stop people from falling asleep, although I don't see anybody falling asleep yet, so that's good. We'll maybe try and see if there's any questions from the audience. Oh, brilliant, there are actually hands up, that's great. I'm gonna go, you can go first, yeah. The lights are in our faces, so it's actually quite hard to see.
Thanks for this panel. It's very interesting.
I don't think it's on yet. There we go.
Thank you for this debate, very interesting. Really enjoying it. So I have a question. I'm Hussein from CSCS. So my question, in the race of developer ever larger AI models, we are seeing multiple organizations repeatedly train similar foundation models from scratch, despite the enormous carbon and compute cost involved. How can the HPC and AI community shift from this redundant model building mindset towards shared, reusable, and sustainable AI infrastructure?
Who wants to? Okay.
Okay, so there's a famous quote, variously attributed, all science is either physics or stamp collecting, right? You may have heard it before. One of the things that's really happened that's exciting in the world of machine learning is the triumph of stamp collecting, right? Fields make progress when data is well curated. AlphaFold was a victory, not just for DeepMind, but for PDB, right? PDB is what made it possible. The answer to the question is open source. That's how we build on top of each other's work. It's why open source is important in general, but it's particularly important to reproducible computational science because it allows us to scrutinize what's been going on. That's why I'm even more passionate about open source in the context of research than I am in other areas. In the world of machine learning, open source doesn't just mean open weights. It means open training data to allow us to compare those things. So finding and working as communities to build good, high-quality data sets. This is why I made the stamp collecting joke at the beginning, right? Good, high-quality shared data sets with good FAIR, findable, accessible, interoperable, reusable data properties, addressing all the intellectual property issues and so on that there is around some of the origin data for AI models, will enable genuinely open source, both open training data and open weights, foundation models for science, which I think when we get there as a community will be really exciting.
I just want to add in the healthcare space, the difficulties of coming to these sort of shared models because of the, private health information and how we deal with that.
Yeah, that's why the trusted research environments question. And you can be FAIR with data even when you can't be genuinely open, if it's people's health records and so on.
Right, but you can be FAIR with models too, right?
Yes.
So I think data, as you mentioned, are what is typically not shared when open source models are released, but the model should also be fair. So FAIR as well in complement to their data, yes.
Okay, thank you for your question. I think you had your hand up over there.
So thank you very much for the nice panel discussion. I was wondering, since you mentioned Alpha Evolve, the influence about these big players and especially companies somehow makes me unnerved maybe, because I've noticed the large impact that they now also have on my professional life that I'm starting up. For example, the utilization of the large language models such as ChatGPT, and I'm wondering what sort of is your idea on how we can combat as a research community to make the similar ideas more quickly available, or I'm still not sure how to deal with them personally because they offer large benefits, but the costs might, in terms of long term, be huge. So that's.
If I may take this, because I brought up Alpha Evolve, and please compliment, I'm sure I cannot cover it all. I think we cannot compete. I don't think we can compete. And for that, I don't think we should engage in a competition, but I think we should engage in remembering and identifying what our strengths are in academia. And in academia, even though we live in a publish and perish environment, we don't live in quarterly deliverables and in quarterly earnings world, right? So I think we don't have to develop a product and make other people rich at the end of every 3 months. But I think we can take the time, which is a luxury they might not have unless they're privately funded by somebody visionary, to take the time and really help the world and not themselves and their stakeholders. So I think we do have that opportunity, and I think we have to remember to not maybe consume our energies in competing with companies, collaborating with them when our values align, and the benefit is for everyone rather than just for them. And I think we have to remember our strengths and play on those, on creativity, intelligence, and not having to deliver a product for the world in 3 months.
Is there another question? Sure there must be. Okay, there was down here. Oh. Okay, yeah, sorry. Yeah, you go there because you've already walked all the way around.
Maybe you stand up
yes.
next time you have a question.
Thank you for the nice discussion. So my question would be more on how many supercomputers do we need? So we have been building these massive supercomputers, and it almost feels like it comes out of a sense of competition. Mm-hmm. And in some sense it feels more fair and just if you have maybe smaller systems which are more accessible to larger fraction of the population. So yeah, just something on that.
Interesting.
Can we make an analogy with laundry machines? They consume a lot of laundry, washer and dryers, right? So they consume a lot of power, and almost everybody uses them. So if we had fewer, would that be better? I'm not saying everybody should have their own supercomputer. I think we have to have the right amount, and your question is very correct. How much is the right amount? I know that there is competition around, but I'd like to think that we are building a supercomputer, for instance, in Switzerland, in Germany, in every country that everybody represents, for the needs of the local communities, but that shouldn't be at every university either, or at every department chair. So,
I think also I'm from an angle that sometimes competition is good in terms of that, because the different supercomputing centers, want to showcase what they're doing. There's also a sovereignty angle now. I guess each country wants to have their own ability, and especially in the era of LLMs, where there's cultural and language specialties. So having just one system, I understand your point, but in a weird way, I can imagine that there is a friendly competition and a thing which actually encourages growth. So.
Yeah, I mean, I think it's unfortunate about the macho flops, right? But I would like to build organizations that are more recognized for the brilliance of the culture they create for data stewards and research software engineers and data scientists and research infrastructure engineers and research managers, as much as for where we are in a list. Although I want to be higher up in the list.
At least in the field of climate science, right now my answer would be as many as possible. Mainly because, as we discussed some time ago, access to data. So those with centers with supercomputers, having the simulations, the models being produced, as long as they're not being shared equally throughout the world, especially to places or countries that are vulnerable to the impacts of climate change, we will keep needing supercomputers everywhere, in every corner of the world. So the question is, how do we resolve this issue of data sharing before we talk about how many supercomputers we need?
I also think that it's important to benchmark, in the different domains and in your particular problems, the ones that do need the larger resources to make sure that the right problems are going on the right machines.
Yeah, that's always the sysadmin argument, isn't it? Someone who's filling up the whole system with 1,000 little jobs rather than one big job is.
And most of the systems that we need to model in order to address those challenges, right, are complex, multi-component, not just multi-physics systems, but multi-social science, multi-environmental science, we're starting with language modeling to get to grips on using computational methods to understand how discourse works, how persuasion works, is a critical part of addressing these challenges. And so it's not, it's all of those different pieces together.
I think you had your hand up.
Harking back to the topic of personalized medicine, I don't know a lot about it, but it sounds like an application that even if we would be able to have the computational power to do it, it would be really hard to pass the legal barrier. Because what about clinical trials? Why would a patient accept a drug without it having been tested, which takes so many years? So then what's the point of accelerating it with AI? I don't know if you have any thoughts about that.
So, the point that we're not there yet is that the computational models would have to be much more accurate for us, because you couldn't do clinical trials on extremely personalized medicine because it's N of 1. So the computational methods do need to be more accurate to go that way.
It's part of computational science growing up as a field is learning to be, if not enthusiastic, at least accepting of working within compliance regimes, right? It's hard to do things. It's even harder to do things when you're working in a compliance regime. That's just true of all engineering, right? And so the work we're doing on trusted research environments, the work in all of these personalized medicine spaces and so on, we're going to have to get used to more legislated environments and still keep the joy of playing with models and computers.
Good.
I kind of had a follow-up question to that. I mean, especially there was an example about Protein Data Bank, for example. I see that as like very nice database, and it's not really like specific to a person. It's more like everybody has a situation, so there's no ethical concern about it. But when it comes to personalized medicine or some other medical applications, you still need data, and data will come from the patients or healthy people, and that's also, I think, a cause of like an ethical concern as well. What do you think about that kind of barrier? Because maybe it's not a good thing to share these information. Maybe the traditional method in this case would be a better option rather than use of AI or other tools. What's your thought on that?
I mean, so, as James was mentioning, the ways of making, the computing safer and, models more reliable without access to all of the information. I think that there's just loads of promise in, you know, what we can do in personalized medicine and digital twins, but there is the issue of data security. But it's issues that will have to be worked out if we want to progress in that area. But a lot of like traditional drug discovery in medicine is like, oh, we tried this and it worked. Like they don't really understand exactly why. So I think that, you know, even if we're using these sequences of kind of like common genetics and not people's individual stuff, like there's still lots of room to improve the accuracy of how we understand stuff, which is going to be with computational models, because we can't do all the experiments on humans that would make us understand everything to that detail.
Any other question? Yes.
So I think my question is related to goals 6 and 12, and maybe others. So it's about the embedded consumptions of all these clusters and data centers that we are all the time building bigger and at a very fast pace. So I think it was, I heard a lot of time, software improvement can be a better investment than hardware replacement. So since we are all scientists, we know we are in a finite world, so at some point this competition for better hardware, it needs to stop at some point. So how do you see these problems in the future? Because at some point, like, we cannot build just bigger and bigger machines. At some point, it has to stop. So what's next?
Okay, so I didn't plan this, but it just turned out that I bought a system for my group in 2016, at the end of 2016, and they were still using it. And of course, you know, because I'm trying to get some funding to get some newer machines, but it's been since 2016, so it's 9 years, right? And yes, we receive comments from the reviewers that, oh, your system is old, what about trying to run on the more newer machines? But I think we need a community understanding that we can't just chase the future, we need to appreciate the present. And the present is built on the past investments in finances, in the materials used to build the hardware that we paid for in the past. And I think, you know, really, it's if I can sum it up to all that, you know, don't stop chasing the future, because you have no future if you don't appreciate the present, which was built on the past. And that is in the academic sense of results and infrastructure and methods. And I plan to buy now a smaller system, because that's how much funding I have, and grow it responsibly and use it for as long as I can. Because first of all, I won't have a lot of money in the future, but also because I don't want to, even if I had it, I don't want to replace it every so often. I'd like to extend the lifetime of the machines. And for instance, in Switzerland, that's also the case at the Supercomputing Center. PISDYNE has been used for much longer than other systems and has produced incredible science for that long period of time. So I think many centers in the world are taking this approach as well. And you, of course, you're right to raise this point.
I think it's also a question, though, probably of recycling and things like that. Because you could have a similar analogy with cars. You could say, don't replace your car, just keep using your own car. But newer cars have better efficiency, and, you know, so it's more around how you probably recycle the materials and help that flow.
Yes.
I think given that, you know, newer hardware is typically more energy efficient, not moving to it, there's a sort of maybe false economy there, but I think being wise on the way you use it and focusing on extracting the maximum. Like you said, so many people just run jobs on systems just to burn the allocation they have so that they'll get another allocation. Because if they underuse the allocation, they won't get it again, which is the most wasteful possible thing. And we know we all do it.
But let's not lose track of, as well, of the value we can and do create with these things. I mean, for me, we've got the world, you know, the whole world has gone through the transition from wilderness to garden, right? Humanity is now large compared to the planet, and we've got to have to work out how to make the careful decisions to manage this very, very, very complicated system, right? This is not naive geoengineering, right? It's really hard work to understand the ways in which we understand the complex trade-offs, the unintended consequences, and all of that for us to live safely while we are large compared to the planet, right? Using that sort of physics and language of is A large compared to B. That requires the kind of things we can do with these capabilities. So long as we use it wisely and efficiently, it's very much worth those costs for me.
Okay, well, I think we will have to close the session there because we have to move on to the next thing. But I'd like to thank very much for being on the panel, and if everyone could give their round of applause to the people. I guess we need to get off.
I'd like to thank you, the panel, and you, Neil, for the fantastic job that you did. And yes, you need to leave apart from Sally.
Okay.
Thank you.
Stay as we move into the awards component of our wrap-up. So I think, Sally, you will come up here now. And the stage is yours, Sally.
Okay, thank you. And I'd like to thank everyone that stayed here with us through the end of the conference, and I'm excited to talk about our Best Paper Award. First, I would like to mention that we had 18 papers accepted in our paper tracks, and the proceedings will be freely accessible via the ACM Digital Library. And so the best paper was selected based off of a committee that included myself and Sherry Lee, who was my co-chair for the papers program, and also our area chairs from where our paper was selected. And so I would like to invite to stage to accept the Best Paper Award on behalf of her team, Kate Arneson. She is a research user interface and experience designer at the National Center for Supercomputing Applications at the University of Illinois Urbana-Champaign. She previously worked at the Pacific Northwest National Laboratory and Mayo Clinic. Through close collaboration with partners across academia and industry, NCSA supports projects ranging from chemistry and healthcare to social impact and data visualization. Combining multidisciplinary backgrounds and areas of expertise, the design team at NCSA focuses on applying human-centered methodologies to the creation of software products. In her paper that she presented yesterday, Towards More Usable, Reproducible, and Sustainable Scientific Software, the Impact of User-Centered Design and Research Software Development, Kate and her co-authors, Li Fu and Lisa Getz, share insights on the role and importance of user-centered design, highlighting case studies from Alpha Synthesis, an open-source software suite for chemistry research. Close collaboration with scientists, engineers, and end users leads to the creation of usable, reproducible, and sustainable applications, advancing the role of design in interdisciplinary research. Thank you, Kate.
Well done, Kate.
I'm sorry.
We continue now with the ACM Poster Awards, and I invite on stage Jay Lofsted from Sandia National Lab, who is the chair of this competition.
So the first poster awards we want to give out are the ones for the ACM Student Research Competition. For those that aren't aware, ACM runs a research competition every year for students across all disciplines within computer science. And there was only one representation out of HPC, and that was coming from the Supercomputing Conference. PASC last year initiated a second candidate that comes from our field. This year, we had a very competitive field, and the way that it works is we get 3 finalists at the undergrad level and the grad level if we have them, and then we have them have presentations that then ends up selecting who the top 3 are and what ordering they have in order to decide who gets to represent at the annual competition. In this case, we only ended up having 1 candidate for the undergrad award. The rest, their posters were not good enough, and because of that, we had our judging for that came down to making sure that the quality of her work was good enough that she deserved to go on. And through the poster presentation and then the final presentation, Patricia proved that she was up for that. So Patricia, please come up so we can give you the award for the best undergrad poster. Then for the graduate awards, we had 5 total posters that made it through the initial qualification period. Then they got down selected to the 3 top in the poster session that we had last night. And then this morning, they went and presented again to a smaller group, and we had an interactive question and answer with them so that we could rank them based on their qualifications in terms of communication, knowledge of their domain, and ability to communicate effectively. And through that, we ended up having these 3 finalists, and I'll do them in reverse order. So Merv, if you come up first. Yeah. So Merv got 3rd place. This is right. All right, and our 2nd place award went to Nicholas. It is really just coincidence that they're both from America and North Carolina. That was not planned. And our 1st place award goes to Sonali. She competed with us again previously with us last year, and also did very well, but this year she managed to take home the top prize. With that, I want to first remind and thank everybody that participated with this, that we're going to do this every year. If you have students that are doing quality research, please have them participate in the student research competition. They can do the regular poster session as well, but if they're part of the student research competition, SIG HBC will sponsor travel, and PAST can potentially waive registration fees. And this is, again, visible through all of computer science through ACM. So it's a really good opportunity to get your students to get really good visibility. And if you are a student, just please contribute and participate. So thank you to all the participants. Thank you to our winners that we have here, and look forward to seeing you all at the next poster competition.
Thank you, Jay, and congratulations again to the finalists and to the winners of this competition. Now we move on to the best poster awards, and those are the ones that you voted. And we have 2 winners. Carla, who presented the GPU accelerated matrix decomposition and selected inversion for bounded arrowhead matrices.
Well done, Carla. Well done. Excellent. Well.
Congratulations. And also Emily from EPFL, who presented Python automatic translation of Python prototypes to C Fortran production codes. Congratulations.
Well done. Well done. Yes, right. Okay, I think that's, we're nearly done. That's the end of the awards. Now just some closing remarks from Laura and I to wrap up before then the exciting announcement at the end of where we're going next year. So basically a lot of thank yous, which are very well deserved. First of all, thank you to everyone who contributed, everyone who gave talks in the mini symposia and the talk sessions, our keynote speakers. We've both discussed throughout the last 3 days the very, very high quality of all of the talks and contributions, and the posters as well. We won't forget the posters. So thank you to everybody who contributed. Thank you to the scientific committee. So these were the poster panel committee, the papers committee, all of the committees that basically put the technical program together, peer-reviewed all of the contributions. We wouldn't have had the core of the conference without them, so thank you to the scientific committee. Thank you to ACM, the SIG HPC ACM for the travel awards, which enabled various students to come who maybe couldn't otherwise have attended, so that was fantastic. I'll do one more, Laura, and I'll hand over to you. And thank you to the interview team who've interviewed various of us, including Laura and I, throughout the 3 days, and our photographer. So thank you very much. And then Laura, you can do some more thank yous.
Yes, thank you to the volunteers who helped run this conference smoothly, and I hope they also enjoyed their time during the conference. And then big thanks to the organizing team who also helped us during the whole process. We had meetings with them every other week. Very enjoyable, all of them. I think we didn't feel like it was a really heavy task, thanks to you, especially to Tatiana and all the rest of the team. So let's give them a big, big thank you. Also very grateful to all our sponsors. And then now we move on to learning that the next edition of this past conference is going to be not far from here in Bern. And Dominic will tell you more about it.
Thank you, Laura. Thank you, Peter.
Thank you. Good luck.
For chairing this excellent conference, past 2025. And I have the honor and great pleasure to invite you to past 26, which will be hosted in Bern. My name is Dominic Obrist. I'm professor of cardiovascular engineering at the University of Bern. My co-chair, who unfortunately is not be able to be here with me today, is Elaine Rayborn from Sandia National Labs. Now, as an overarching theme for next year's conference, we chose to focus to look at building trust in science through HPC co-design. As we all have experienced in the past years, maybe months, science is increasingly being questioned. And I think it's a good point in time to think about how HPC can do its share to build trust in science, to make sure that people believe what we do, believe in our results. How can we use co-design, so the collaboration between different individuals, different teams, many different disciplines, different expertise? How can we work together to get better results, to validate our results, to make our results trustworthy? How can we how can we use co-design to position HPC for future demands on scientific trustworthiness? So a few examples. AI in medicine. We have seen a few talks also in this conference. Think of the end user at the medical doctor who's using our tools. Think of the person who even goes beyond that, the receiver, the patient. How can we integrate them in our design process? How can we integrate them in our work to make sure they believe the results, they understand the results, they understand the models? It also applies to weather prediction, climate modeling. How can we validate our results in a way that people understand, that people believe in our models, in our results? This does apply to energy assurance, security. epidemiological and disease modeling, how do we communicate our results to these people. This is all something where we believe HPC co-design can help, and it's a good time to think about this. I'm pretty sure that all of you will be able to map your particular application, your research question to this overarching theme. How can we build trust through HPC co-design? As I told you, my co-chair, Elaine Rayborn, was not able to be here, but that you at least get a chance to see her, well, a bit live and at least hear her. Here's a pre-recorded video of Elaine.
I'm Elaine Rayborn from Sandia National Laboratories, and I'm very excited to co-chair PASS 26. Our theme is Building Trust in Science through HPC co-design, and we're very excited about this theme, and we want to hear from you. We hope to see you at PASS 26 in Bern, and I hope you have a safe journey home.
Thank you, Elaine, and I can only repeat that. I'm looking forward to see you all in Bern. Bern, arguably the most beautiful city in Switzerland. So please be there in 1 year. I think the date is June 29 to July 1st, so 2 weeks later than this year. And with that, I finish here. Wish you safe travels back, and looking forward to see you again next year, PASS 26 in Bern. Thank you.
With this, thank you all for being here until the very last minute after these 3 fully packed days. I hope you enjoy them as much as myself and Peter did. Safe travels back, and Bern is indeed beautiful. It is beautiful.